In this video, we're going to talk about kind of the foundations of calculus and what it means to find instantaneous versus average. So when we're talking about the average rate of change over an interval, then it's similar to what we learned in Pre-Calculus 1. It is your you've got two ordered pairs, so you have x sub 1 and x sub 2, which are your 2 points, the x points. You put in x sub 1 into your function and you get an output. You put in a y or an x sub 2 in your function and you get an output. So the average rate of change is going to be the change in y over the change in x, which is f of x2 minus f of x1 over x2 minus x1. Or if you are moving some distance h from your original point x sub 1, moving to the right, so we have x sub 1 plus that distance h you have moved. So this is similar to the x sub 2, and then of course you have f of x minus 1 all over the difference, which is h. So this is similar to saying this is y2 minus y1. Therefore, we have the delta y, and then of course we have it over delta x, which also gives us the difference quotient, which is f of x plus h minus f of x all over h, where h is the difference between x2 minus x1. It's how far you traveled from one point to the next point, where x sub 1 is on the left and x sub 2 is on the right. Now, when we are asked for the average rate of change, what we are doing is finding the slope of the secant. What the slope of the secant is 2 points on your graph, and then the line that is formed that goes between those 2 points, that connects those 2 points. So that's this line right here. Oop, that's not what I wanted to do. That is, let me see, this line right there. And then, of course, as the distance that you have traveled, this is the distance traveled. So the distance you have traveled between x and a, that is h. And then, of course, as h goes to 0, then the secant line becomes the tangent line. So in general, what we say is the secant is the line that passes through the points a, f of a, and x, f of x. Or you might see this as x sub 1, f of x sub 1, and x sub 2, f of x sub 2. And then, of course, the slope of the secant is the same thing as the difference quotient, which we're familiar with from Pre-Calculus 1. And then, of course, as h goes to 0, we end up with the instantaneous instead of average, and we now have the tangent line. So if we're asked to find the average rate of change over the gambit interval, then the first thing you're going to do is find the f of x sub 1, which is going to be f of 4, which is the square root of 4, which is 2. We're also going to find f of x sub 2, which is f of 25, which is the square root of 25, which is 5. Now, the average rate of change is the slope of the secant, which is equal to f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. In this case, this is going to be 5 minus 2 over 25 minus 4. We end up with 3 in the numerator and 21 in the denominator, in other words, 1 over 7. Let's go ahead and take a look at our next example here. With our next example, we're going to do the same thing. We're going to find f of x sub 1. This is going to be equal to 2 plus the cosine of 0, which is 2 plus 1, which is 3. And then f of x sub 2, which is 2, plus the cosine of pi, which is 2 minus 1, which is 1. So the slope of the secant, which is the average rate of change, is going to be f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1, which is going to be equal to 1 minus 3 over pi minus 0. So we get negative 2 over pi. Now, let's just talk a little bit about what we ended up with as answers. Because this is a positive answer, that means that the average rate of change is increasing. It's not increasing at a very high rate, but it is increasing. And because this is negative, the average rate of change is decreasing. And it's decreasing about, not quite 1, but it's pretty close. It's decreasing at a faster rate than this one is increasing. So let's take a look at average velocity here. So when we're talking about the average velocity, what we're really trying to do is we're trying to find the slope of the secant at two particular points of time as the particle or the item moves with respect to time. So if we're trying to find the position of the ball dropped at the top of a 200-meter tall building given by this equation, where this equation tells us where it is, how much it has traveled with respect to time. S is distance with respect to time. N is measures in meters. And we want to find out what it is between 4.99 to 5. So what we're going to do is we're going to get our calculators out and we're going to do f of x sub 1, which is going to be 200 minus 4.9 multiplied by 4.99 squared. We're also going to find f of x sub 2, and we're going to do the 200 minus 4.9 multiplied by 5 squared. And then we're going to find the slope of the secant. So this is for A. So then we're going to find the slope of the secant, and this is going to give us our average velocity from 4.99 to 5. And when you do the calculations, you end up with negative 48.951. And then you do B as well. So we're going to do the slope of the secant or the average velocity. Now I'm going to use 5 and 5.01. And I calculated it out to be a negative 49.049. So let's do C, slope of the secant, which is the average velocity, which I calculated to be negative 48.9951. And then let's just do D. So that is the slope of the secant, or the average velocity, V, which is equal to, I got that one to be negative 49.0049. And what you're going to find as you get closer and closer to 5, that the numbers on the left side of 5, so this one is the 4.99999 and then 5. And this is the right numbers, which is the 5 to 5.01. And you're going to find as you get closer and closer to 5 on either the left side of 5 or the right side of 5, that it'll end up becoming the same number as you get closer. So if you were to continue with this iteration process, you're going to end up with having the instantaneous velocity, which is what we're going on next. So instantaneous velocity is at a snapshot in one particular time. How is the velocity changing with respect to time? So if we were to look at our example above here and we were to guess what the instantaneous velocity is for that particular ball at 5 seconds, I would guess that it's going to be 49, because if we take a look at this, a negative 49, this is pretty close to 49, and then as I get even closer on the left side of 5, I'm getting even closer to 49. This is on the right side of 5, and you'll see that this is close to 49, and then even closer to the right side of 5, I get 49. So I would guess that the instantaneous velocity for the ball, using my previous example at 5 seconds, my instantaneous velocity, which is s or v of t, is going to be negative 49. That would be my guess. Okay, so when we are talking about integrations, which is what we'll be doing in this class, what we're really doing when we're doing integrations to simplify what an integration means, and there is a lot of ways to interpret integration, but for us, what we're going to start out with when we start doing integrations at the end of this quarter is the integration is the area underneath a curve. That's how we're going to define it initially, is the area underneath the curve. And to find the area underneath a straight line, regardless if it's increasing, decreasing, or constant, it's pretty straightforward. It's just the basic shapes that's formed between the x-axis and the line. But when it's a curve, it's a little more difficult to figure out what the area it is using geometry. So what we're going to start out with is taking our curve and breaking it up into rectangles, and then finding the area of each one of those rectangles and adding them up, and that's going to approximate the area underneath the curve. But what we are going to be doing is we're actually going to be doing the integration. We will start out with this part here, which is the breaking it up into rectangles, and then we will do the actual integration when we can. There's going to be times in calculus, especially in pre-calculus 2, in which you won't be able to integrate directly, so we will learn other ways to integrate and to find the areas under the curves, or whatever the application is. One of the applications is, of course, finding the area under the curve. So if we take a look at our function here, which is 1 minus x squared, and we're going to sketch the graph over the interval from -1 to 1, and we want to estimate the curve using rectangles of width 0.5, 0.4, and 0.2. So the first thing we're going to do is we're going to draw the curve. So to make my life easy is I'm going to make each one of these be worth 0.2. So 1, 2, 3, 4, 5. So here's where +1 is. 1, 2, 3, 4, 5. Here's where -1 is. And if I have y is equal to the square root of 1 minus x squared, then I have y squared is equal to 1 minus x squared, which we know is just a circle centered at the origin with a radius of 1. But notice here I have a positive, so I'm taking the top half of that circle. So 1, 2, 3, 4, and 5. So here's +1. So here's my circle. And what I'm going to do is estimate the curve by using rectangles that have the width of 0.5. Now, if I have a rectangle of width of 0.5, then I'm going to have 4 rectangles. So starting out with the width, which is equal to 0.5, then I'm going to have 4 rectangles. I'm going to have the first one, which is going to be -0.5, so 2, 4, -0.5. So here's my first rectangle. And then my second rectangle is going to be here. And then my third rectangle is going to be 0.5, and so it's going to be like this. And then my fourth rectangle is going to be just that. And you can see that by using rectangles, and I'm using what we call the right-hand side, that this green represents the rectangles. And to find the area of my first rectangle, so here's the area 1, that's going to have a width, which is 0.5, and then its height is going to be the square root of 1 minus -0.5 squared. And so the area of my first rectangle is going to be 0.433. I'm going to find the area of the second rectangle, which is again going to have a width of 0.5. But now I have 1 minus this 0, squared, the square root, is equal to, well, it's just going to be 0.5. Now, the reason that I am using negative 0.5 and 0 is because, like I said, I'm using the right-hand side. So I'm figuring out what the height is, and to find the height right here, I'm going to put in 0.5, negative 0.5 to find the height. I put in 0 to find the height here, and then I'm going to find the height on this one. Because of symmetry, that when we do a sub 3, it's going to be the same thing as a sub 1 because of symmetry, and so we have 0.533. Now, the area total is going to be the 4.33 multiplied by 2 and then plus the 0.5. So I end up with, let me see, times 2 and then plus 0.5. So I end up with 1.366. Now I'm going to do this again, and now what I'm going to do is I'm going to cut it up into 0.4s. So I have 0.4. So here's my first one. So here's my first rectangle. And then here's my second rectangle. And then here's my third rectangle. And then my fourth rectangle. And then my final rectangle. As we explore this idea further later in the quarter, we're going to discover that sometimes we're going to have less error when we use the left, the right, or the midpoint. So right now, though, we're just going to use the right just because I can, and it's not telling me any other way. So let's go ahead and find the area sub 1, which is going to be my width, which is 0.4. And then I am going to multiply it by the square root of 1 minus. Now this is negative 0.6, so I'm going to use negative 0.6 squared. And so I'm going to put that in my calculator, so 0.4 times the square root of 1 minus negative 0.6 squared, and I end up with 0.32. Now I have two of them because we see that this rectangle here matches this rectangle here. So I'm going to call this a sub 1, and then also a sub 4 is also going to be 0.32. And then I'm going to do my next one, which is a sub 2. It has a width of 0.4, and it has the square root of 1 minus. And then my right-hand side is negative 0.2, so negative 0.2, the quantity squared. And I get 0.391, we'll go with 19. Now, it has the same height as the next one, which is a sub 3. So it has the same height and width as the next one, which is a sub 3. And so a sub 3 is 0.3919. And so using 0.4, my area total is going to be 2 multiplied by 0.32 plus 2 multiplied by 0.3919. And I end up with 1.4238 approximately. Now, if I were to do it for the third time, where the cut that I'm using is going to be 0.2, I'm going to find that I'm going to be even closer to the actual value. And so what we're going to be doing in this class is we're going to be exploring this in depth later in the quarter. What we're going to start out doing in the beginning of the quarter is really looking at spending a lot of time on the instantaneous velocity or the slope of the tangents. We're going to spend a lot of time looking at the slope of the tangent. We're going to call that the derivative. So that's pretty much what the introduction to calculus. We're going to spend, like I said, we're going to spend some time doing the integrations, but mostly we're going to be doing derivatives in this class, which is the slope of the tangent.